Alright, so I'm going to build on the video that you saw on Khan Academy earlier this week, and we're going to just take everything that Sal Khan said and continue on from that point. I'm just going to highlight the most important component of this fundamental theorem of calculus part 1. And so you had a picture like this where we have a function f of t is my x-axis, and what we were trying to do is calculate the integral of that function from some interval from a to x. Okay, so it was this area is the area we were trying to find. And we want to do away with our idea of Riemann sums for now because we know that that's one way that we could handle this. But what Sal Khan stated is that we're going to call this function big F of x. Okay, so we'll call this its own function. And what the fundamental theorem of calculus says is that if I want to take the derivative of that function, so if I want to calculate d big F with respect to t, that's going to be the same thing as calculating the derivative with respect to x of that function that we were just given. Right? So far, all we're trying to do here, or in other words, I could call this f prime of x, right? So if I want to calculate the derivative of this function, which is f prime of x, that means I need to take the derivative of this, because this function is this expression. When I take the derivative of this expression, I'm going to be left with a really simple expression. So it turns out that that's going to be equivalent to f of x, this function right here, as a function of that variable there, right? As long as these two variables line up. So the idea behind this is if I have an integral and I'm asked to take the derivative of that integral, what I'm going to be left with is this function right here. It's sort of like saying take the antiderivative of this and then take its derivative. Well, if I take the antiderivative of a derivative, I end up exactly where I just started. All right, so we'll see an example of this now. So we're given a function g of x, and it's defined as an integral. And then we're asked to find the derivative of that function. So what I'm trying to do here is calculate g prime of x. And what that means is to take the derivative with respect to x of that function right there, from 0 to x of the square root of 1 plus t squared dt. According to the fundamental theorem of calculus, what this is saying is that if I want to take the derivative of a function that is represented as an integral, what I'm going to be left with is 1 plus x squared as my final solution. And to put this into context with something like what we've seen before, remember, we've said that position, velocity, and acceleration are all sort of like ladder functions, right? Our position function, you could call this big V of t, because we've referred to it as the antiderivative of velocity before. But another way to express V of t is f prime of t, because the derivative of position is velocity. Also, I could call v of t big A of t, right, because it's the antiderivative of acceleration. But I could refer to acceleration as v prime of t or s double prime of t. A lot of different ways to talk about these functions, right? So what if I said that I'm starting off with a velocity function here, and I'm told to take the antiderivative of that function? And then after that, I'm told to take the derivative of that function. I'm just going to end up in the exact same place. And that's what the fundamental theorem of calculus part 1 is telling us. It's saying take the antiderivative of a function and then take its derivative. If you do that, you're going to end up with the exact same function that you had. You just have to keep in mind the variable that is within that interval from a to b that we're talking about. Okay, so now one more, a little bit more complicated example. We're asked to find the derivative with respect to x of this integral from 1 to x to the fourth of secant of t dt. Okay, so the tricky thing here is that part of our interval is a function itself, and we're going to need to account for that. So first, let's keep in mind what are the things we've been given. All right, so we know our function, f of t, is secant of t. And we know that our a is 1 and our b is x to the fourth. Since b is a function, we're going to make a little substitution here. So we're going to say that u is x to the fourth. We're going to replace that x to the fourth with just the letter u. Now, if that's true, then remember, du dx is going to be 4x to the third, because that's like saying take the derivative of this u function with respect to x. So this is something that we're going to need to keep in mind. What we want to think about here is this whole thing is like a chain rule situation, where our outer function is this integral, and our inner function is this x to the fourth. So we're going to be executing a chain rule here when we take this derivative, right? We're going to take the derivative of the outer function, and then we're going to multiply it by the derivative of the inner function, just like we used to do with chain rules. So when I take the derivative with respect to x of the integral from 1 to x to the fourth of secant of t dt, that's like saying take the derivative with respect to u of 1 to u of secant of t dt times du dt. And that's just applying the chain rule. Remember, we're taking the derivative of the outer function, and then we're multiplying it by the derivative of the inner function right there. So according to the fundamental theorem of calculus, this part of this expression is an easy one to evaluate, because that is equivalent to f of u. And then we also have this du dt as well. So another way that I could write this is secant of u times 4x to the third. And that's because if this is du dt, we already expressed that that is 4x to the third. And remember, f of u is going to come from this original function. If f of t is secant of t, then f of u is going to be secant of u. So we've made a substitution there. Now here's our expression where we can just make one more little substitution, because we know what u is equivalent to. That's just going to be secant of x to the fourth, because u is x to the fourth times 4x to the third. So therefore, we can make the statement that the derivative with respect to x of the integral from 1 to x to the fourth of secant of t dt is equivalent to, and I'm going to put the 4x cubed in front, times secant of x to the fourth.